This segment we're going to talk about steady flow reversible work. So we have an equation for reversible boundary work, and that's typically associated with a closed system. So it's the integral of PdV. But now we're going to develop an expression for reversible work for a steady flow process, which is in an open system. So here I've got just a generic open system. I've drawn my control volume, and for an open system, you've got mass going in and you've got mass going out. So if I apply my first law and I've got an open system, so I start with the equation for the first law for an open system, the dE dt equals q dot minus w dot yada yada yada. Well, if it's steady flow, the dE dt goes away and the m dots can divide. If it's got one inlet and one outlet, the m dots just divide through, and I get things in terms of the equation that you see here. Now I'm going to put things in differential form. So I've got some differential amount of heat transfer for the reversible process minus some differential amount of work for the reversible process. And I remember back when I talked about the entropy change for developing an equation for the entropy change, when we talked about Clausius's inequality, we came up with this equation right here. I believe we had it in terms of big Q, but here it is in terms of little q. So now I've got an equation that I can replace that differential amount of heat transfer for the reversible process with. So I've got TdS, and I'm going to just kind of bring some stuff on one side of the equal sign to solve for that differential amount of work, because that's kind of what I'm after. And then that TdS, when I think back of what my TdS equations are, I had one in terms of dH, I had one in terms of du. I'm going to do the one in terms of dH because I can get rid of that dH term in this equation here. So the dH is, I got dH minus dH, so those go away, and I'm just left with three terms. And now I'm going to integrate it. So I get the expression for the work for a reversible process equals negative integral VdP minus delta kinetic energy minus delta potential energy. And typically those kinetic and potential energy changes go away, because the place where we often use this equation right here is to calculate work for a pump that is operating at steady state and reversibly, which would be an isentropic process. And an isentropic process is adiabatic, and for a pump, typically these guys are insulated because the only energy you want crossing the boundary is in the form of work. You don't want it crossing the boundary in the form of heat transfer. So adiabatic and then reversible, and now we have an equation for reversible steady flow work. So the other nice thing about a pump is the specific volume is approximately constant, because you're either compressing a substance from a compressed liquid to compressed liquid, or compressed liquid to a saturated liquid. So it's all in that liquid region, and the specific volume is not going to change that much. It's an incompressible substance, or can be modeled as such. And so that pump work, which is isentropic pump work, is equal to negative VdP. Or the integral of VdP. And I'm going to ignore the kinetic and potential energy changes as I typically do with a pump if I'm just analyzing the pump itself. And because the specific volume is constant, that comes right out of the integral. And I have a nice simple equation that I can use to calculate pump work for an isentropic process if it's at steady state, which typically in this class we are at steady state. So where this can be used is when you calculate isentropic efficiency for a pump. So we said the isentropic efficiency of a pump, it's the work for the isentropic process over the work for the actual non-isentropic process, which we put in terms of H1 and H2 and H2S. But now I have another equation that I can use to calculate what the isentropic work is, and that's that VdP equation, or negative VdP equation. So I've got another way. I don't have to calculate that H2S, and it just saves just a little bit of time. So, all right. Well, I hope that was helpful. Thank you for watching.